I try to cluster our clustering tools. So right now we have these 5. The story began with Word, which is a hierarchical similarity-based clustering approach. I won't talk about Word today. Then came Jarvis Patrick, which is non-hierarchical, also similarity-based. These two were born in 2002. I'm not going to talk about Jarvis Patrick today. Then came library MCS, which is somewhat different because it's structure-based. In its name, MCS is for maximum common substructure, but actually what it does, it searches for the maximum common edge substructure. But I'm not going to explain this because right after my presentation, Oleg will give a nice talk and I'm sure he will elaborate on this topic, so I leave it for him. In the past couple of UGMs, I introduced library MCS, talked about its features, also gave some data on how its performance increased over the years. I think I never really did that to give a demo, but now I try. Just a very brief one. So this is our website, ChemAxon.com, where there is a demo page for library MCS. As you see, it's still stuck at version 0.7, and soon I will explain why this happened. I mean that in the last year or last 1.5 years, you didn't see any major improvement in library MCS. If you click this, it's going to start with Java Web Start. That means that you don't need to download anything, you don't need to install anything on your computer, but it will work. When you start library MCS like that, it will load the default data set just to make interested potential customer's life easier. He or she does not need to find a data set. But this is not a particularly interesting data set. This contains 1,000 randomly chosen structures from the Maybish screening collection. So I would show you something else which may be more interesting. I have a couple of data files here. Let's start with this small one. The input data set contains some data. This is an SD file, and library MCS offers this choice in this dialog to import data associated with the structure. So we will import this data. Okay, and the clustering is done. It was fast because this particular set contains only 87 structures. That's not much. So it didn't took even a second. And in these brief statistics, we see that there are altogether 4 levels. As I said in my introduction, a library MCS is hierarchical. And on the top level, we found 26 clusters. Now, these are the interesting ones because these are what we call the scaffolds. These are these MCSs or MCESs. Structures that are present in the data set and are common to more than one input structures. There are some guys here at the end which didn't share any such common substructure with the others. These are the singletons. And you can use this simple GUI to browse through your cluster data. There's this hierarchical view called the dendrogram tree. You can navigate and then corresponding structure will pop up. So on this bottom layer, you find the input structures, and if you go up, you will see this structure was shared by this one and that one. And then here there's what we call a hierarchical SAR table, SAR table, because here you see the scaffolds that the algorithm identified along with corresponding data imported from the input file with some statistics. So for instance, let's see the smaller one. There was a cluster that contained 3 elements. This was the common structure shared by these 3. And you get the statistics here that the C log P of the input structures was found in this range. The same for rotatable bonds and so on. So that can be quite handy. There are other views using the Marvin gridback view that Julie presented today. So you can click on one level and then see the scaffolds along with the singletons. Okay, so we can challenge library MCS with a somewhat bigger and more diverse file. Some D2 inhibitors. Now we have 500 of them. This time it took 1 second to cluster them. We didn't have now data associated with the structures. But still, you can browse this hierarchy using this hierarchical table and see how clusters were formed with these common cores. Okay, perhaps just one more, an interesting one. This time 1,000 elements, and this file contains a mixture of several combinatorial libraries. And you will see that in an instant the algorithm was able to identify excuse me, the scaffolds that were present in the combinatorial libraries. So this time 3 libraries were mixed, and these are the 3 cores along with around which the library was designed. So this much about library MCS now. And I move back to my presentation slides. Recently we implemented Bemis and Markov frameworks, and please correct me if I don't pronounce the name of these guys properly. I'm always confused. Okay, thank you. Now, these frameworks are quite similar to this MCS thing, but less mathematical, is more for chemists. These are much easier to understand and explain. Much easier to compute, a lot faster, yet they are really useful. So we implemented these frameworks, and it's already released in 5.2, I think, maybe sooner. And I'm going to demonstrate these now. Just let me show the next slide, because that's the real topic of this presentation, the new JKlustor. Now in the JKlustor package, we used to have Ward and Jarvis Patrick and library MCS, but all these were standalone monolithic codes. And when we challenged the million compounds libraries and wanted to implement newer algorithms like Bemis and Markov and more, we found the need for a lot more sophisticated, better designed framework, software framework for clustering. And this is what's new in JKlustor, a clustering engine. I put on this slide to scare the chemist and perhaps give some meat to chew on for the more IT people. And based on this new engine, I will demonstrate how Bemis and Markov works. So this is a server in Budapest, and on this server I will launch a clustering, a Bemis and Markov clustering, using just 8,000 randomly chosen structures from the Zinc database, and start this clustering server. So the server started. As I said, it's running in Budapest, but we can access it via the web in a simple HTML interface. It should come alive, yeah. So the server reports the result of a Bemis and Markov clustering. As you see, the clustering method with Bemis and Markov. In total, 8,106 input structures were clustered. And here we get a brief statistics that there were several singletons and so-called real clusters that contain more than one element, and these cover 78% of the input data. And then you can immediately save this if you click this button or icon. You can save your clusters, but you can get a much finer resolution statistic. Okay, so the overview in the top, and then a very detailed coverage along with these line bars. And with this, I like the last column the best, because with this you can get a very important first insight into your data set. So you can say that roughly 8% of the total clusters cover 43% of your data. So it's like a Pareto analysis. You will see that this refresh is very slow. Okay, so I won't wait for it. Yeah, as I said, data comes via the internet from Budapest. So you would see here that roughly 40% of all clusters covers 60% of the data. Okay, now you can look at the clusters. There must be something wrong with the internet. The server is running. Oops. Okay, if the page doesn't load, I won't wait for it for long. Okay, then I move on. Sad, because now we can't see the Bemis and Markov frameworks. Very true, okay. Then I move back to my presentation. So based on this architecture, we implemented Bemis and Markov, and just recently sphere exclusion. My plan was to demonstrate sphere exclusion via the internet, but there are always technical problems. Sphere exclusion is non-hierarchical, similarity based, and the reason why we implemented is that it can cope with very large data sets. So over 1 million compounds, as I said a couple of years ago, we tried to challenge these really large databases. So I won't give a demo on sphere exclusion now. And finally, as a summary, let me give you an overview what comes next. This new engine will be released in 5.3 along with the sphere exclusion algorithm. Another quite well-known and popular algorithm, the k-means, will also be part of 5.3. We will also implement diverse subset selection when you feed in your data and you want to have just 100 or 1,000 or whatever, a small number of randomly picked compounds that are as diverse as possible. The new library MCS, which will be based on this new architecture, will come in 5.4, and that will contain some novel features, like it will be able to find so-called non-connected or disconnected MCSs, and that's something that, again, Oleg will talk about. We will also implement something what we call micro APIs. These will serve very specific needs. So the user who wants to implement a certain application based on clustering will not face a huge API with thousands and thousands of methods, but there will be tiny task-specific APIs, a lot of them, that contain just very few functions. So, for instance, for diverse subset selection and so on. For us in the future, the key issue is integration. As you saw, Bemis and Markov frameworks are already integrated in JChem for Excel. They are also available in Instant JChem. Now, based on this new architecture, all clustering algorithms we have and will have will be instantly available in Instant JChem as well as in JChem for Excel. But for me, most interestingly and importantly, also in JChem base. This was Cheesy's great idea and his brainchild that we should always give a default clustering in each and every JChem data tables, because then the user can browse the data without any filtering. The user can have an immediate view of the data, for instance, using the Bemis and Markov frameworks. So this should come in 5.4. And finally, thanks to the great colleagues who worked on JKlustor, Gabor is now the guy whose main job is the new clustering engine, and he was the software developer who implemented this new software architecture. Thank you for your attention, and please ask your questions.
Great, thank you. Question there.
Miklos, with Bemis and Markov clustering, is it the case that two compounds are in the same cluster if and only if they share the same Bemis-Markov
exactly.
framework?
Yeah.
And for each compound, there's one Bemis-Markov framework?
Yes.
Okay.
Yeah, the nice thing about it that with these frameworks, you don't need to compare two structures against each other in a pairwise fashion. That's why it's very sweet and fast. Okay, thank you.
Okay, great. Let's give him one more round of applause.